ZLW and ZLL. Okay. So let's see, I erased this. I got to put Z sub W back up here, don't I? What was Z sub W? That was L minus 2 lambda. Right. And let me write down what Z sub L was also. Z sub L was W minus a lambda. Okay. So what is Z sub WW? Zero. Yeah, because you look at Z sub W, there's no W in here. So that's 0. A Z sub LL is equal to 0. Z sub WL, okay, you take the derivative of this with respect to W, and that would be 1. And that's also, by the way, Z sub LW is also 1. By Young's theorem, we know those things are going to be the same. Okay, so now we have enough to plug in. Let's find out what this is. We wanted to take the determinant of 0. G sub W was 2, wasn't it? G sub L was 1, 2, 1. Z sub WW was 0. This was a 1, 1, 0 there. Okay, so let's, hopefully this will turn out to be positive. Otherwise, I'll be embarrassed. Okay, because we want a maximum. I'm confident that gives us the maximum. So we expand across the first row. So this is a 0, so it just drops out. But the next term, we make it a minus 2 times its minor, which is 2, 1, 1, 0. And then you take this term next, 1, times its minor, which is 2, 0, 1, 1. So let's see. This gives us 0 minus 1 times the minus 2 gives us 2. Plus 1 times 2 minus 0 is another 2. So that is 4. It's positive. So that guarantees, Jacob, that we have a maximum at the values of W and L that satisfy the first order conditions.
Okay. Well, how would we say the interpretation for lambda here?
Good question. Very good question. Who can tell? Let's write our Lagrange function again. Our Lagrange function is this: Z equals WL plus lambda times 64 minus 2W minus L. Who can tell me what this value of 16 means?
It represents the change in your area. In this problem, your area can be considering a change in your constraint.
Right, exactly right. So in other words, lambda star is always this. It's the derivative of your whatever it is you're trying to maximize. In this case, A. It's the derivative of A with respect to whatever your constant is. Okay. Now, in this case, A stands for area. So really, you could say it's the change in the optimal area, the optimal value of the area, for a slight increase in your constant. So in other words, this means, roughly speaking, approximately, if you had 1 more foot of fencing, how much extra area would you get? Yes, you would get to 16 extra square feet of area if you have 1 more foot of fencing. Now that's an approximation, but that should be approximately right. Okay, so the optimal value of the Lagrange multiplier tells you how sensitive your optimal solution value is to a slight increase in whatever the constant is in your constraint. And here the constant is 64 feet of fencing. Okay. Yes?
Just out of curiosity, can the Hessian value here ever be equal to 0?
It could be.
So we have to do a third order.
Right, yeah, then you don't know. The second order sufficient conditions just tell you what you have, if it's positive or if it's negative. If it's 0, you don't know what you have. You have to do some further testing. Yeah, it's kind of similar to classical second order conditions. You have to do some further work to figure out what you have there.
Just wondering if there's no unique solution, right? So there's multiple solutions for WL?
Not necessarily. Not necessarily. Generally, your bordered Hessian will generally turn out to be either positive or negative. It's pretty unusual for it to be exactly 0. But if it did turn out to be exactly 0, then you wouldn't know. You'd have to do some further testing to figure out what you had. Okay. Any questions over this? Obviously, your optimal area here, your A star, would be 16 times 32, which is what, 512? Is that right? Josh, did you have a question? No. Okay. Okay. All right, so you're ready for the quiz then. But Jacob, that was a good question that you asked. That was a very good question. And I'm glad we went over this again, if nothing else for Gray's benefit, because he wasn't in 641 when I discussed this. Okay. All right, here's today's quiz.